Hey everyone, happy Tuesday. Hope you're doing well. Miss you guys a lot. Just wanted to talk to you today about 4.3. Again, we're going to talk about derivative tests. But first, we're going to talk about something that you guys saw in AP Stats, or if you weren't in AP Stats, you would have seen it in FST, or even in Standard Stats. Any stats class you take, at some point you talk about normal curves. And in AP Stats especially, they bring up this equation of the normal curves, and it is an ugly one. It's got an e to a power that involves a lot of fun symbols here. And what's going on here is that mu is the average of the normal curve, and that sigma is the standard deviation of the normal curve. And you may remember that those have a very important place on the graph. The average always happens right in the middle of the graph. So you see all of these have an average of 0, except for this green guy over here, which has an average of -2. That's the center of your normal curve. And the standard deviation, that has to do with how spread out the graph is. Notice the orange one has the widest standard deviation. That's why it's so flat. The area under the curve is always 1. Because the probability density distribution has to give a total probability of 100%. There is a specific distribution that is used most often. It's the one that has all the tables. And the cool thing is that the translation from one to the other is very smooth. But the point is, I want to talk about this standard normal curve. So the formula that we had, it can actually be boiled down, because what the standard normal curve does is it puts the average right at 0, and it makes the standard deviation 1. So our average is 0, the standard deviation is 1, which makes this formula a lot nicer to work with. It's still not beautiful. We still have this 1 over the square root of 2 pi. Where the heck did that come from? But we have e to the negative x squared over 2, which is much more manageable, because that sigma went away because it was a 1, and that mu went away because it became a 0. So what I want to show, and you might have actually learned this in AP Stats, they might have briefly mentioned it, the place where you're 1 standard deviation away, what happens there? Well, it looks like we're kind of coming upwards. If we were driving along the curve, maybe, remember this from yesterday, so we're driving along the curve, we'd be turning left, left, left. Where do we start turning right? I bet it's right at that inflection point. I bet that happens exactly 1 standard deviation away. The cool thing is, no matter what your average and standard deviation are, that always happens. That exactly 1 standard deviation away, that's where you have the inflection points of the curve. We're going to prove it for the standard normal curve. It's a good little bit of bell work today. So we're going to take this function, we're going to show that it has a horizontal tangent at 0, and that's a maximum. And we're also going to show that it has an inflection point at -1 and 1. If you want to pause the video and try that on your own right now, so that required taking some derivatives and proving that we have a horizontal tangent here, and that the second derivative changes sign at those 2 points, you can go ahead and do that, and then you can come back and we can go over it, or you can just go over it together with me. Alright, so maybe some of you had an option to do this. Let's see if you were able to figure it out. So we have our f of x. Let's try finding f prime of x. So f prime of x, well, this is just a constant. 1 over root 2 pi. So I'm just going to forget about that for a second, and we're just going to deal with this e to the negative x squared over 2. So e to the x is just its own derivative, so I'm just going to leave e to the negative x squared over 2 alone. Then I have to multiply by the derivative of the baby. So x squared over 2, that's just 1/2 x squared. So the 2 comes to the front, so it'll be negative 2x over 2. And then we have to leave that constant out in front, 1 over the square root of 2 pi. We can make that look a little prettier. So bring this to the front, the 2's cancel. Looks like we have negative x over the square root of 2 pi multiplied by e to the negative x squared over 2. So e to any power is always positive, no matter whether the exponent is positive or negative, because e to the x looks like this, always has positive y values. So that's always positive. So the only thing that is determining the sign of this entire derivative is this guy right here. So the x is the only thing that's determining it. So it looks like this whole derivative, f prime of x, is equal to 0 when x equals 0. So x equals 0 is our only critical point. Hey, that's right here. And it looks like when x is less than 0, if x is less than 0, then it's going to be a negative of a negative, which gives us a positive. And we see that it's increasing up until 0. And then after, we're going to have a negative. So we're going to be decreasing off to infinity. So that proves that at x equals 0, because we have a sign change in the first derivative, that is indeed a maximum. Cool. Now let's talk about those inflection points. This is going to be a little bit trickier. So our second derivative, what do we have to use here? We have x times e to some power. Looks like a product rule problem. So let's pretend that this is our first function and this is our second function. We're going to have to use product rule. So f double prime of x, let's do the derivative of the first thing. That's just going to be negative 1 over square root of 2 pi. And we leave this guy alone, e to the negative x squared over 2. Then we're going to add to that. We're going to leave the first guy alone, so we have negative x over square root of 2 pi. We'll take the derivative of the second thing. We've done that before, right? That's just this thing that we did up here. So that's e to the negative x squared over 2 gets left alone. We multiply by the derivative of the baby, which turns out to be negative x. So it looks like if we get all our ducks in a row here, we can factor some stuff out. So we factor out this e to the negative x squared over 2. We can also factor out a 1 over 2 pi, root 2 pi. And what we're going to have left in here, this is looks like a negative 1. And then over here, it looks like we have just a plus x squared. So that factors out to x plus 1, x minus 1. And that shows that we have zeros here at x equals negative 1 and x equals 1. And we can even see that it's going to change sign at those points because we have two single roots here. So if we go something less than negative 1, we're going to have something here that's positive altogether. Have something in between negative 1 and 1 where it's going to have negative. And then if we have something after 1, it's going to be all positive. So we have concave up, concave down, concave up, and those inflection points at negative 1 and 1. I've wanted to do this problem with a calculus class like my entire life, and I had never done it until today. And I'm really glad that it ended up being pretty cool and working out. Now, if you want to try some more stat stuff, this is a challenge problem. I completed this today during my conference. We had a break, and I just was craving some math because we had been doing so much talking and feelings sharing, which is great, but I wanted to do some math. So I gave this a shot. This is the general equation for a normal curve with an average of mu and a standard deviation of sigma. Try taking the first derivative of this and proving, because it doesn't have to be at 0, so we have an average now here at mu. So prove that at mu we have a maximum when x equals mu, and then show that these 2 points, this is going to be mu plus sigma, and over here we're going to have mu minus sigma. Prove that those 2 points give inflection points. This is a challenging problem, but give it a shot. It's not impossible, and any of you guys could definitely do it. All right, let's move on to what's new today. Oh, not yet. Sorry, I lied. I wanted to talk about one more thing with concavity, because the car driving is a really nice analogy, but there's one more way that you might hear concavity discussed, and it's one thing that comes up every once in a while in an AP problem. So a couple ways to think about it, and they both involve tangent lines. So this is definitely concave down. This is definitely concave down. And something we know about it now, that means that f double prime of x has to be less than 0. Let's draw in some tangent lines. Well, if I could draw in tangent lines. That one's 0. And then we come down as we come down. So that first one I'm going to fix a little bit. It should be a little steeper. There we go. So I'm going to just kind of, well, first I'm going to fix that one. I'm going to kind of approximate what the slopes are of each one of these tangent lines. And it's not going to be perfect, doesn't have to be perfect, but it's going to be close. So the slope here might be 1, then maybe this is like 3/4, maybe this is like a half, well, this might have been better as a half, maybe this is like a quarter. Here it's 0, and then over here we have a slope of like negative a quarter, and then here it's like negative 1/2, then like negative 3/4, and this is like negative 1. What do you notice about these numbers? What's happening to them? We started at 1, 3/4, 1/2, 1/4, 0, negative 1/4, negative. They're decreasing. They're decreasing. So the slopes of the tangent line, slopes of the tangents are decreasing. And this is a place that people sometimes get into trouble. People, and we're going to have a warning slide at the end of this whole presentation today, but they say things like the derivative is increasing or the derivative is decreasing. You have to be really careful about language like that, because in this case, yes, the first derivative is decreasing, and that shows that it's concave down. Because if the first derivative is decreasing, right, f prime f prime in this case is going to be, let's see, it's going to be positive and it's going to be negative. So it's going to go through the axis like this. So it is decreasing the entire time, but you have to be careful because sometimes you say the derivative is doing things when you really mean to be talking about the actual function f of x. So you just have to be careful. But yes, the slopes of the derivative are decreasing. And that's another way of saying that f double prime is less than 0. Because if the derivative is decreasing, our second derivative has got to be less than 0. Another thing you'll notice is where are all of these tangent lines in relation to the curve? Oop. Where are all of these tangent lines in relation to the curve? They're all on top, right? All of these tangent lines are on top of the curve. What if we draw them in down here? Where are all these tangent lines? They're below the curve. That's another way of talking about concavity. And usually AP will ask a question like, at this point, does the tangent line lie above or below the curve? And what you'd have to do is find the second derivative, prove that the graph is concave up, and therefore the line is going to lie below the curve, which is kind of cool. But let's look at the derivatives here. So it's like -1, maybe like -3/4. Here it'd be like -1/2, maybe -1/4. This is 0. Then we have +1/4, +1/2, +3/4, and +1 here, maybe like +1.2 or something there. What's happening this time? We start negative and positive. That whole time our slopes are increasing. Okay, so here the slope of the tangents are increasing. Another way of defining concave up. We also know that the second derivative there is greater than 0. I love these because it's like a puzzle. It's like a puzzle. You are given the information you need, and there's a very intimate relationship between f of x, its derivative, and its second derivative as far as concavity and the slope of the function, which is kind of cool. All right, now, gosh, 12 minutes in, and we're starting finally the lesson for today. Thankfully, today's lesson is not very long or very complicated. So the first and second derivative tests. Now, I don't want to say the bane of a calculus student's existence, but it's challenging when to use these accurately. You never need to use them, but they are a nice kind of a slick way to show an AP grader, hey, I really know what's going on. So let's take a look here and see what these tests are. So remember, first of all, that critical points are the only places, and endpoints are the only places that maxima and minima can happen. So if we check all of our critical points, some of them are not going to be maxima or minima. These guys right here are actually inflection points, go from concave down to concave up, and here it's up to down. But any place that we do have a max or a min, we're either going to have an undefined derivative, or we're going to have a slope of 0, or it's going to be an endpoint. Right, here our absolute min is an endpoint. We have a local min at our endpoint on the right, but then all of our locals in between, and actually our absolute max as well, happen at places where the derivative is undefined or 0. So that's going to be important for when we talk about the derivative tests. So, first derivative test at a critical point. First thing you got to do, you got to find all the points where f prime of x is equal to 0 or undefined, because those are where you're going to have your critical points. Once you do that, you're going to do this derivative test to see if f prime changes sign. So that was what we were doing yesterday with the number line, right? You find all your critical points, let's call them C1 and C2, and then you do that sign analysis. So if you do sign analysis and you find that somewhere it changes from positive to negative, like this spot right here, you know that's a maximum, because a function must go from increasing to decreasing. So if it goes from increasing to decreasing, that's a max, right? Whether it's a nice 0, or maybe it's a cusp or something. So if we go from positive to negative, it might be something like this, maybe a corner. But we went from positive to negative, and that is the only way you can have a maximum. That's the only way you can have a maximum, is if you change from positive to negative. That means that we have a maximum value at that point. So first derivative test, you can say because f prime changes from positive to negative, by the first derivative test, we have a maximum at that point. Let's take a look at another one. So this is another one at a critical point. This time we're going from negative to positive. So maybe we have our critical point here. We go from negative to positive. That means the function must go from decreasing somehow to increasing at that point. It might be a corner like I drew. It might be a cusp. Could be a nice smooth dip in the graph. But for sure at that point, if we go from negative to positive over that point, we know that we have a minimum. It's got to be a minimum. It's the only thing that can happen there. Now, endpoints are a little bit trickier, but not really that bad. Let's see what's going on here. They're saying f prime is positive for x greater than a, and f is defined on ab. So we have some function. We have an endpoint a, we have an endpoint b. And they're saying that when x is just to the right of a, we have a positive derivative. Well, if it's a positive derivative, that means the slope is upwards. That means this must be a minimum. And that's all it says. So if we have an endpoint, and just after that endpoint we have a positive derivative, it must be a minimum. It's the only thing that could happen, because it's increasing. We have nothing on the other side, so it doesn't have to be a 0, right? It could look like this. We could have a here, and it could be coming up like that, right? But it has a positive derivative to the right. So x greater than a, not greater than or equal. You don't test the derivative at a, because derivatives at endpoints are weird. But just after it, we've got a positive derivative, so we must have a minimum at that point. Works the other way as well. So this is an endpoint at the other end. So here's our a, here's b. This time they're saying, well, what if the derivative is negative leading up to b? Well, if the derivative is, this time the derivative is positive. So the derivative is positive, which means that we're increasing. So we have an increasing derivative up to b. That must mean that b is a maximum. So just kind of stuff that makes common sense here, right? Not too bad. If you're increasing up to an endpoint, it's got to be a max because you're coming up, 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 and then you stop, right? If it was the other way around, if we had b here, let's say it's increasing for a while, but then it decreases right before landing at b, that's going to be a local min. Okay, so it's all just about thinking the derivative is the slope of the function. Remembering simple building blocks of calculus gets you so far. Derivative is the slope of a function. Tangent line, you need a point and a slope. Simple stuff. Not too bad. So let's take a look at an example. That's really it for the first derivative test. So we're going to find the relative extrema on 0, 2 pi. So we have a closed interval here. So the things we're going to have to check are critical points. And we're also going to have to check endpoints. Endpoints. Whoop. There we go. These are the things we're going to have to check. So the endpoints are 0 and 2 pi. Let's see what we can find for our critical points. So to do that, we have to take the derivative, f prime of x, which is just 1/2 minus cosine x. So we have to figure out when that's equal to 0. That's going to happen when 1/2 is equal to cosine x. We're going from 0 to 2 pi. 0 to 2 pi, cosine, we need a positive 1/2, so it'll be on the right. That'll happen up here at pi over 3. That's where cosine is the shorter distance, that's 1/2. And down here at, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pi over 6, which is 5 pi over 3. So those are our two critical points, pi over 3 and 5 pi over 3. So now we have to do our analysis. So we're going to label all our points, start at 0. Then we have pi over 3, and then 5 pi over 3. And then we have 2 pi over here. So let's try something between 0 and pi over 3. Now we're checking here, we're checking the first derivative. Because if the first derivative is positive here, it means the graph of the function f of x is increasing. If it's negative, it means the function is decreasing. So let's see what's going on. Let's try, like, I don't know, pi over 6, which is right here. That's between 0 and pi over 3. So we do pi over 6. Cosine of pi over 6 is root 3 over 2. So we would have 1/2 minus root 3 over 2. 1 minus root 3 is like negative point, was it negative 0.4, negative 0.7, something like that. So it's going to be a negative number over 2, so we have a negative value there. Then in between, well, let's do something easy. Let's do where cosine is 0. How about right at the top of the circle? Or the bottom. Any one of those points on the left will work too. But cosine is 0 up here at pi over 2. 1/2 minus 0 is positive. Then between 5 pi over 3 and 2 pi, I don't know, maybe like 11 pi over 6, that's where we're going to have a cosine value that's bigger than 1/2. So 1/2 minus cosine of 11 pi over 6 is going to be negative. And that's all we have to do. So we see the function must go from negative to positive. Maybe something like that. And then we're increasing, 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 and then back to negative before we get to 2 pi. So it might be like something like that. I don't really know. I have it ready to go on Desmos, though. We'll take a look. So let's see what's happening here. What we're saying is that we have a minimum at x equals pi over 3. Why? Because f prime of x changes negative to positive. That's the first derivative test. Then we have a max at x equals 5 pi over 3. Why? Because f prime of x changes the other way around, positive to negative. How about at our endpoints? What's going on at 0? Well, it looks like if it's decreasing that entire time, we must have a max. So we got a max at 0, if I could write. Max at x equals 0. And we have, at the end here, we have a minimum at x equals 2 pi. I don't have room for my justification there, but that's because the derivative is negative coming off of 0, and it's also negative coming into 2 pi. So we must have a maximum at the beginning and a minimum over here at the end. And that's both all because of the first derivative test. So when you're writing on your AP problem, you can say there's a minimum at x equals pi over 3 because of the first derivative test, which says since f prime of x changes negative to positive, that's where we have a minimum. So first derivative test is a nice thing to throw in there just to say, hey, I know what's going on here. You can't just show the number line. You have to either say f prime of x changes, or you have to mention the first derivative test. Let's take a look at the next one. So our next problem here, we've got x squared minus 4 raised to the, I wanted to look at the last one on Desmos. I said I was going to do that. Let's take a look. So let's look at that function, 1/2 x minus sine x, and let's see what it looks like. And here it is. So we see we have that minimum at pi over 3. We have a maximum over here at 5 pi over 3. We also, since we're restricted, we have a local max at 0. And then when we end at 2 pi over here somewhere, we're going to have a local minimum. Cool. All right, back to it. So let's look at that next example. This time we have x squared minus 4 raised to the 2/3 power. So we have no endpoints here. We're not defined on an interval. We're defined on all real numbers here, I think, because there's nothing that you're not allowed to plug into that function. And let's see what it's going to look like. So our derivative, I always change to red when I come back. So our derivative, f prime of x, is going to be, well, we're going to have to use chain rule here. So we'll have 2/3, leave the inside function alone, x squared minus 4, raised to the, you got to subtract 1 from that. It's going to be the negative 1/3 power, multiplied by the derivative of the inside, which is 2x. So we want to know when that's 0 or undefined. Well, to do that, I might write this a little bit differently. We're going to have 2x times 2, which is 4x, upstairs, right? 2 times 2x. Then underneath, we'll have 3 times the quantity x squared minus 4 raised to the 1/3, or the cube root. So we'll be in trouble when this denominator is 0. So if the denominator is 0, that's going to happen when x squared minus 4 is equal to 0. That happens when x is plus or minus 2. So those are critical points we're going to have to check. Negative 2 and 2. We also have to check when it's 0. Well, it's 0 when x is 0, right? The top of the fraction has to be 0, so if 4x is equal to 0, which happens when x equals 0. So negative 2, 2, and 0. Set up our number line. Negative 2, 0, and 2. So we talked something before, between, and beyond. So before negative 2, let's try like negative, I don't know, negative 3. So negative 3 upstairs gives us a negative on top. And then on the bottom, if we have a negative 3 squared is 9, minus 4 is positive 5. Cube root of 5 is going to be positive, so on the bottom we have a positive number. So negative over positive gives us a negative. Between negative 2 and 0, I don't know about negative 1. Negative 1 will give us a negative 4 upstairs. And on the bottom, let's see, negative 1 squared is 1, minus 4 is a negative number. Cube root of a negative will stay negative, so we have a negative on the bottom as well. So negative over negative gives us a positive. Between 0 and 2, how about 1? Positive upstairs now, because we have positive 4. On the bottom, we have 1 squared is 1, minus 4, yep, negative 3 again, so we have a negative on the bottom. So positive over negative gives us a negative. After 2, how about 3? Positive upstairs, downstairs, 9 minus 4 is 5, so we got positive downstairs as well, so we have a positive. So relative extrema, let's see here. We go from decreasing to increasing to decreasing to increasing. So it looks like we have a minimum at x equals negative 2 and x equals positive 2. And we have a max at x equals 0. Now, I am perhaps being a poor calculus teacher and not doing the y coordinates. Almost 100% of the time, they ask for the x coordinates. They're very specific when they want the point. And we could find it, right? If you plug in the values here, -2 and 2 both give you 0. So that would be -2, 0, and 2, 0. And at 0, when we plug in 0, we have 4. Whoops, sorry, up here. We have 4 to the 2/3. 4 to the 2/3, that's the cube root of 16. So that would be, let's see, what are we at? 0, comma, cube root of 16. Okay. And we know that these are justified by the first derivative test. First derivative test. Test. Okay. That's kind of the swanky way to say it, but you have to make sure you know what you're talking about. Otherwise, you could say f prime changes negative to positive at -2 and at 2. F prime changes positive to negative at 0, and that's also legitimate justification. Let's talk second derivative test. So, warning I'm going to give you right away about the second derivative test has nothing to do with inflection points. This is a very, very common mistake. Nothing to do with inflection. Because people often, they're asked to find inflection points. They say, by the second derivative test, this must be an inflection point because the second derivative changes sign. No. First and second derivative tests are both about extrema. They're both about extrema. It's about finding maxima and minima of the function. And let me show you how this works. Let's take a look through here. So they tell us if f this only happens at critical points. So we only use this when f prime is 0. So we know we have a horizontal tangent. So one of three things could happen. If we have a horizontal tangent, it could be that you have a maximum, right? There's a horizontal tangent there. It could be that you have a minimum. There's a horizontal tangent there. Or it could be a pass-through like that, where you have a horizontal tangent right through there, and it's an inflection point. So one of those three things has to happen if we have a horizontal tangent. Nothing else could be happening. Okay? So, the first case, f double prime of c is greater than 0. Well, we learned yesterday that means we have a graph that's concave up. Only one of these three graphs is concave up. Which one is it? It's this one right here. So if we have a concave up graph that has a 0 derivative, it's got to be a minimum. It has to be minimum. There's no other way that could happen. Try to draw a graph that has a horizontal tangent line that is concave up that isn't a minimum. It's impossible to do. It's impossible to do. So that's our first case. Our next case is, hey, if it's concave down, it must be a maximum. So what we're basically doing here is we're creating some possibilities. So if you have f prime equals 0, f prime of x equals 0, and then you show f double prime of some value is less than 0, well, we've got to have a concave down and a horizontal tangent. You can say by the second derivative test, that's a maximum, and you're done. All you have to show is this, that you have a horizontal tangent line and it's concave down, because there's nothing else that could be happening there. It's got to be a maximum. Let's look at an example. So we've got, I don't know if I skipped one, nope. So I've got a function here, it's a polynomial. They want to find the relative extrema now. And we're going to use the second derivative test instead of having to do that rigmarole of the number line. So let's find f prime of x. That's negative 15x to the fourth plus 15x squared. Looks like we can factor that. Let's pull out a 15. Let's even do a negative 15x squared. So pull out a negative 15x squared. We're left with just x squared minus 1. So that's negative 15x squared times x plus 1 times x minus 1. Difference of squares there we can factor. So our zeros are 0, negative 1, and positive 1. Now, we could use the first derivative test. We could make the number line, and we could find out whether we change from increasing to decreasing or what's happening here with those values. But let's use the second derivative test and see if we can figure it out that way. So let's do f double prime over here. So f double prime of x using our standard form here is going to be negative 60x cubed and then plus 30x. Let's factor that. Let's pull out a negative 30x. So that gives us a positive 2x squared minus 1. So we don't have to find the zeros. We're not looking for inflection points here. all we need to do is find out, okay, this is where we have horizontal tangents. So something's going on at 0, we have a horizontal tangent. At -1, we have a horizontal tangent. At 1, we have a horizontal tangent. I'm going to use the second derivative to find out if it's concave up or down at those points. 0 is easy. I plug in 0, and I get f double prime of x equals 0. So that means we've got a horizontal tangent there, but we must be dealing with an inflection point, because it's not concave up or down, so it looks like we're dealing with an inflection point there. The second derivative test does not tell me anything. Let's plug in -1. If I plug in -1, I get positive 30. Multiplied by -1 squared is 1. Times 2 is 2 minus 1 is 1. So we are concave up at -1. Well, if we're concave up at -1, up like a cup, we must have a minimum. So -1 is a min by the second derivative test. That is terrible handwriting, I'm sorry. So it's a minimum by the second derivative test. And let's see what's happening at +1. So I plug in +1, I get a -30 times 2 minus 1, which is 1. So that is less than 0. So at +1, I have f prime of x equals 0. F double prime of x is less than 0. So there must be concave down. So I've got a max. So we have shown by the second derivative test that at -1 we have a minimum, and at 1 we have a maximum. That's all there is to it. Kind of cool. One more for you. And if you guys want to try this on your own, why don't you give it a shot? So try to find the first derivative, figure out when it's 0, and then find the second derivative, and use the second derivative test to prove whether we have maxes or mins at the places where you found critical points. Give it a shot. All right, welcome back. Let's try it together. So we got f of x. Let's do f prime of x over here. F prime of x is going to be 6x to the 5th minus 15x to the 4th. So we got 6x to the 5th minus 15x to the 4th. And so we want to find out when that is equal to 0. So let's factor out, looks like we can factor out a 3x to the 4th. So I have 3x to the 4th multiplied by 2x minus 5. So it looks like our spots here we're going to run into trouble are going to be at 0. Not trouble, but it's where I have a horizontal tangent line. And also at x equals 5/2. Those are two spots where we're going to have horizontal tangent lines. So let's find f double prime and see what's going on at those points. F double prime is going to be 30x to the 4th minus 60x cubed. Looks very similar to the last one. So let's factor out a 30x cubed multiplied by x, and then it'll be minus 2. Okay, not concerned about finding zeros of that. I just want to plug these in and see what's going on. 0 gives me a 0 for the second derivative. So it doesn't tell us anything about 0. That 5/2, though, if I plug that in, it'll be positive here. 5/2 is 2.5 minus 2 is also positive. So at 5/2, I know f double prime of 5/2 I just showed is greater than 0. And we know f prime of 5/2 is equal to 0. So we have a horizontal tangent and a concave up graph at 5/2. So we must have a minimum. And that was justified by the second derivative test. Now, we'll caution you about things like the x equals 0 here. Because if you have a function like, I don't know, f of x equals x to the 40th power. X to the 40th power is going to be very, very flat right there. But it's going to come down and up kind of like a parabola. If you take the second derivative of that, that is definitely a minimum, right? That's a minimum. But if you take the second derivative, you're going to have, let's see, 40x to the 39th, and then 40 times 39x to the 38th. If you plug in 0 here, it's going to give you 0. But that's not an inflection point. That is a minimum. So it's always prudent to check to see if you have a change in sign at those points in the first derivative. Because if you have a change from negative to positive, that's going to guarantee by the first derivative that you have it working. So second derivative does not exclude things. It only proves to you if you do have a second derivative that works out, that's where it's going to work. It's going to be good. So what you can do is you can check the sign change at the point for the second derivative. I'm using way too many. I'm confusing all of you, I'm sure. So let's set this up for 0. So we have f prime of x. Let's just look at 0 for now. And we have f double prime of x. Let's just look at 0 for that one too. So if we look at what's happening on f prime at 0, f prime of x I've got right here. So 0 on something on the left of 0, like negative 1. Negative 1 to the fourth is positive. So this is going to be positive on the front. And then we have negative 2 minus 5 is negative. So we have a negative going in. And then after 0, which I like 1, we have a positive, and then 2 minus 5 is still negative. So we go from a negative to a negative. So it was decreasing, and it continues to decrease. Nothing going on there, right? Let's see what the second derivative is doing. Second derivative, if we plug in something before 0, like negative 1, that'll make negative on the front end, and then negative 1 minus 2 is negative. So negative times a negative is a positive. And then after 0, let's try 1. 1 cubed is 1, and then 1 minus 2 is negative. It goes positive to negative. So what happens here? We have an inflection point. So at 0, it goes from decreasing to decreasing, but we must go concave up to concave down. So you have an inflection point that goes through the axis. That's how it's possible that we have a first derivative of 0, but our second derivative is also 0, which means that we might not have a sign change in the first derivative. So you can always show that by using the number lines. Cool. So, warnings about justify your answer. Just be very careful about the words that you choose. If you say second derivative test or first derivative test, make sure you know what you're talking about. If you say something like the first derivative is positive, make sure that's what you want to say. Because a big habit that people get into, if this is f of x, and you're trying to show increasing, decreasing, they'll say, hey, after this, after x equals 0, they'll say the first derivative is increasing. Well, that's not true. The graph is increasing, but it's possible the first derivative isn't increasing. In this case, it actually is, but it might look something like this. Okay, so natural log x, the first derivative is always decreasing because the tangent lines are getting shallower and shallower. The function is always increasing. So f of x is increasing because the derivative is positive. Not because the derivative is increasing, because the derivative is positive. So you just have to be careful about how you talk about these things. So some words to avoid. The function. What function are you talking about? Are you talking about f of x? Are you talking about f prime of x or f double prime of x? The graph. Which graph? F prime, f double prime? You don't know. It? Yeah, don't have any idea what it is. It is increasing. What are you talking about? The equation. Okay, which equation? The derivative? Yeah, you can use that, but you have to be real sure you know what you're talking about. If you say the derivative is increasing, that means you're talking about the second derivative now. You're talking about increasing the first derivative. Ugh, that's just a mess. Words to use instead, f of x, f prime of x, f double prime of x. If you tell me f prime of x is greater than 0, I know exactly what you're talking about. That means that the function is increasing. If you tell me that f double prime of x is equal to 0, great. We're probably talking about an inflection point if there's a sign change there. We're not sure it's an inflection point, but it might be. Got to prove a sign change. If you tell me that, I don't know, f double prime of x is less than 0, I know the graph is concave down. So using these things very specifically works great. The equation is increasing. I don't know what you're talking about. Equations don't really increase. They stay the same. They're equal. Graph could be increasing, right? But I don't know what graph you're talking about. F of x is increasing. That helps me out a whole lot more. Cool. So tomorrow, you're going to be doing some AP problems. I've got a packet set up for you, and Mr. Fleming is going to have it for you. You're going to spend most of the hour working on it, and they're hard. Not all of them are that hard. They're not impossible for sure. Then you can do them all. Just remember your basics. How do you make a tangent line? How do you find inflection? How do you find concave up, concave down, stuff like that? I'm asking you to do 4 out of the 6. If you choose to do this one, number 2, and you might want to write this down for tomorrow, don't do letter C. Letter C is something that I didn't realize was on this problem. It's something we'll learn later on. I'm going to post the answers to Moodle, and it will be on there. I'll leave the answer up there if you want to look at some funny symbols. But it's something that we'll learn later on this semester. So, your homework for tonight is on the sideboard. It's also right here. Numbers 2, 4, 5, 6, 23, 24, 33, 36, 38, and 40. Deals with some stuff with the first and second derivative tests. Also, if you did the Benton Avenue video, I haven't gotten any submissions yet, but I bet there's one that's going to come in. You just need someone to ride along with you. I don't want you crashing because you're trying to fiddle with your phone. So just drive through and tell me about your inflection points. Email with any questions you've got. Be happy to answer them, or any problems you have on the video for, well, I might not make a video for tomorrow unless there are questions. But that's all I've got for you. So, the pirates from yesterday. Place to start with this, if you need to go back and check out the problem, you can. The video is getting quite long here, so I'm going to run through this. But they're numbered 1 through 1,000. They know their numbers. They're going to vote whether or not to kill pirate 1,000. If they do kill him, they're going to have 999, 998, until they get down to a place where they can't reach a majority. So the place to start with this is if there's one pirate, he's going to get all the gold. If there are 2, they'll split it, because 2 will vote to save himself, 1 will vote to kill. If there are 3, well, the 2 know that they're safe. So they're going to vote to kill number 3 because they know it'll stop at 2. At 4, 3 and 4 will vote to save number 4 because they know if 4 dies, 3 dies. So 3 wants to save number 4. So at 4 it will stop. So those 4 people know that they're safe all the way down to 4. So they're going to try to kill everybody they can until it gets down to 4. So those 4 people will be able to kill 5, 6, and 7 because 4 people have a majority there. But at 8, these 4 people do not want 8 to die, because if 8 dies, well, he's not happy, and then 7, 6, and 5 will be killed by 4. So at 8, they'll split. You see the pattern? 1, 2, 4, 8. 8 can kill all the way up to 15, but they can't kill 16. Or 16 can't kill 32, who can't kill 64, 128, 256, and 512 is the highest power of 2, less than 1,000. So this is confusing for some people because they're like, that seems like a weird number. But think of it this way. Pirate number 512 knows that he is safe because if 512 dies, the next 255 pirates know that they are dead meat by these 256 people because it will stop when it gets to there. So they're all trying to protect 512 because the rest of them don't want to die. So the 512 is a majority for 1,000, so they'll kill 1,000, 999, 998, all the way until down to 512, which is when they'll split the gold. Cool problem. I love you guys. That's why I'm here. Have an excellent day, and good luck on your AP problems tomorrow. I'll see you on Thursday.